Morning guys, this is lesson 2 of probability. You can find the blank copy in the blank folder on Edmodo. So the word that's going to pop up today is independent. So what does the word independent mean to us as it pertains to life? Well, most of us would probably think it's us living on our own, having our own job, maybe not living with our parents, making our own decisions. But as far as it pertaining to probability, when we use the word independent, we're basically talking about two events that don't have an influence on each other. Dependent events, as far as probability is concerned, is when one event would have some sort of influence on the other event occurring. So two events are independent if the occurrence of one does not change the probability of the other occurring. So let's just say, for a silly example, if it rains, people eat pizza. And we know that these two events really don't have any effect on each other. If it's raining or not, really doesn't, again, have any influence on whether people are going to eat pizza. A dependent event is when one event influences the outcome of another event in a probability scenario. So if it rains, people use umbrellas. Right. So these two events definitely have influence on each other. If it rains, we definitely see more people using umbrellas than if it was not raining. So two events are independent if the probability of event A is equal to the conditional probability of A given B. Now that's a word that we saw yesterday that we will revisit on how to represent probability when we have the word given being used. So this is the statement in words, and now we're converting this statement into probability symbols. So two events are independent if the probability of event A is equal to the probability of A given B, right? So again, that's this statement just put in symbolic form. So for example, if we know that the probability of event A equals 0.3, and the probability of A given B is also equal to 0.3, then A and B are independent events. Which again means that events A and B have no influence on each other. Okay, so now we'll get into an example. Okay, I would pause this right now and read it for yourself so that you can absorb. So number one, find the probability that mom is grouchy. So out of a total of 365 days, it looks like mom is grouchy 73 of those days. Number two, find the probability that mom is grouchy given that it is raining. So we saw this word in our first lesson, and we have to understand that whatever comes after the word given tells us our subgroup, which directly tells us what denominator we're going to be using in our probability. So it is raining a total of 35 days. Of those 35 days that are raining, mom is grouchy 7 of them. Question 3, find the probability it is raining. So out of 365 days, it is raining a total of 35 of those days. Find the probability it is raining given Mom is grouchy. Again, we see the word given. Whatever comes after the word given is your subgroup, which again tells you what your denominator is going to look like. So Mom is grouchy a total of 73 times. Of those 73 days, it is raining 7 of them, right? So if we just go back up to 1 and 2, and we convert these to a decimal, and we do the same thing for 3 and 4, we're going to see that in both scenarios, in both pairs, that these fractions have the same exact value. So type them into your calculator. So 73 over 365, and let's see, 7 over 35, and we see that they are both equal to 1/5 or 0.2. Okay. So the probability Mom is grouchy, how about I represent that as the probability of event G? And then this one, the probability that Mom is grouchy given. So this is the first time I'm going to introduce you to the symbol for given. The symbol for given is simply just a vertical line like this. So the probability that Mom is grouchy given that it is raining, I'll use R for raining, right? So since these were both equal to 0.2, we say that the fact that Mom is grouchy and the fact that it is raining are independent events, meaning they really didn't have any influence on each other. So the fact that it was raining, again, had no effect on Mom being grouchy or not. Same thing down here, if I were to switch it. So 35 over 365 is about 0.0958, etc. And 7 divided by 73 is the same exact decimal. And if we can just rewrite these in symbolic form, we can say that the probability it is raining, we are using capital R for raining, is that decimal. And for this one, the probability that it was raining given, right? So that's our new symbol. The word given is this vertical bar. Given Mom is grouchy, we were using capital G for grouchy. That also had the same decimal. So we can say as well that these events are independent. So notice that here we just really reversed what we did in the first couple of sets of examples, but what it's really important for you to understand is that when you're trying to prove if two events are independent or dependent, the first letter of your given statement matches the letter of your other events. Notice down here that same thing happened. The first letter of our given statement matched this letter. And notice that in the first pair it came out to 0.2, in this pair it came out to 0.0958, but the decimal doesn't matter. What matters about the decimal is that when you do these two individual probabilities, that the decimal comes out exactly the same. So 0.2 is 0.2, 0.0958, etc. is 0.0958, etc. So we can, once again, establish that these two events are independent of each other. Okay? So let's get into number 5. Now, even though some of these words we have not seen yet, maybe we can still answer this question. Sean's team has a baseball game tomorrow. He pitches 50% of the games. There is a 40% chance of rain during the game tomorrow. If the probability that it rains, given that Sean pitches, is 40%, it can be concluded that these two events are. So, I think what I'm going to do is I'm going to use symbols to represent each of these statements. There were actually three probabilities given to us. So how about we use S for Sean pitching? I don't want to use P because then it kind of looks a little weird, right? Then we would have two P's in our probability. So how about we say that the probability that Sean pitches is 50%, which would really be 0.5 as a decimal, all right? There is a 40% chance of rain during the game tomorrow. Okay, so the probability, let's use capital R for rain, is 0.4. And then they gave us another statement. The probability that it rains given Sean pitches is 40%. So the probability that it rains given Sean pitches is 40%. What conclusion can be made? Well, as it turns out, we actually are given extra information that we don't need. If we were trying to figure out if these events were independent or dependent, if we sort of use this as our basis, oh, there's my little baby. If in fact these two events are independent, then the probability of it rains given Sean pitches would have to equal the probability of it rains. That would conclude independent events, meaning they don't have any influence on each other. And the reason why I know that is, again, because the first letter of your given statement has to match the letter on the other side, just like we reviewed up here, right? First letter here, match this letter. First letter here, match this letter. And if we go and use the information provided to us, it looks like that holds true. They told us that this probability was equal to 40% or 0.4. And they told us that this probability was also 0.4, and that checks out. So we can conclude that these events are independent. So the fact that maybe we didn't know what mutually exclusive meant or complements meant yet really didn't affect our ability to answer this question, right? So in conclusion, this we never really needed. Okay, so in our next example, the results of a poll of 200 students are shown in the table below. For this group of students, do these data suggest that gender and preferred music styles are independent of each other? Justify your answer. Let's see, so the first thing I notice is we don't have the total row and we don't have the total column. So that is something that I'm gonna take a minute or so to figure out. So let's see, 54 and 36, that gives us 90. 25 and 40 gives us 65, 90 and 60, oh, excuse me, we have one more. 27 and 18 gives you 45. And looks like this is gonna be 200, which we kind of knew because they already told us that this is a poll of 200 students. Let's see, 36 and 40 is 76 plus 18, I believe is 94, I wanna say. And that would get us to 106 right here. All right, so getting back to the question, it says, so we have to figure out if gender and preferred music styles are independent of each other, meaning there's no influence on your gender and what style of music you prefer. So in these situations, in these Regents examples, what you're gonna do is you're just gonna make up your own combination. So how about for gender, I'm gonna do I'm going to just choose female. And it's really nice to always put the letter that you are using to represent that particular topic, I'll say, or event. And then for preferred music style, you would just do the same thing. You would just simply select one of these preferred music styles. So I'll just keep it simple. I'll choose the first one here, techno. And I'm just going to indicate that I'm going to be using T for techno, right? So, and then you would set up your test for independence. Now again, it's a test for independence. It's not really a formula per se. So let's see. The probability of being female, does it equal, so I'm going to be putting a question mark over here because that's what we're trying to figure out. Does it equal the probability of being female given the fact that we like techno music? So again, I knew that the first letter of our given statement has to match the letter on the other side, right? You could have also reversed it. You could do the probability of preferring techno music. Does it equal, right? Question mark, we're trying to figure this out. The probability of preferring techno music given the fact that we are female. Okay, so we're going to do both scenarios. So the probability of just simply being female. So out of 200 students, it looked like there were 106 females. Okay, equals, but question mark. The probability of being female given the fact that they prefer techno music. So again, whatever comes after given gives you your subgroup. There's a total of 90 students that prefer techno. Out of those 90 students that prefer techno, 54 of them are female. And then what we would do is we would just analyze the decimals. 106 divided by 200, and then 54 divided by 90. So we can see that although the decimals are close together, that they are different. So this is 0.53, which does not equal 0.6. So the conclusion is that these events are not independent. They do have some influence on each other. Let's test it out the other way as well. The probability of selecting a student that prefers techno music out of a total of 200 students, 90 of them like techno music. Again, equals, but question mark. We're trying to test this out. The probability of preferring techno music given the fact that we are female. So whatever comes after given is your subgroup. There's a total of 106 students that are female, and of those 106 students, 54 of them prefer techno. So we analyze the decimals, and you can see that those decimals, again, they are pretty close together, but they are not the same, and that's all we're looking for. That are they exactly the same? And they are not. Okay, so again, notice that the decimals are different in the scenarios, but the important thing is you're recognizing if the decimals are the same to each other or they are just simply different from each other. So the conclusion is that gender and preferred music styles are dependent on one another. And again, when we say that in probability events are dependent, that means that there is some sort of influence, again, on one another. So I'm going to stop this video, and what I'd like you to do is approach 7 in a very similar way, and then in a separate video I will post the results.